In the next example, we'll use the entire real line as a set. So we are going to construct an open cover for the real numbers, the entire real line, as follows. This set, u sub x, is going to be equal to this, which I've defined over here. This basically says it's an epsilon neighborhood around x. We're defining it for every single x in the real numbers. So every real numbers has its own set, capital U. So here's the definition, and I'm going to use this again frequently, probably in the future. Neighborhood, this is an epsilon neighborhood around x. So x is the center of the neighborhood. Epsilon is the width, or more likely the radius, because you're going to the left and to the right. So this is just equal to this interval centered at x, going from x minus epsilon to x plus epsilon. So basically, every single point on the real line has a little interval around it. That one does too. The one right next to it has one. That one has one. That one has one. So clearly, every single point on the real line is contained inside its own neighborhood. So U1 is contained, 1 is contained in U sub 1. The number pi, U sub pi contains the number pi, and so on. So if we union all of these uncountably infinite number of sets together, we get the entire real line. So clearly, R, actually I'm going to say it's equal to U sub x, the union of the U sub x's. I don't know how to, let's see, that's the union. This is U sub x. The union of all the U sub x's where x is in the reals. So R is equal to this. They're exactly equal, which means that R is contained inside this union. Right? Every set is a subset of itself. So if these two are equal, then R is a subset. So the sets, the collection of sets, is an open cover for R. Well, I don't think we're going to be able to find a finite subcover, but we can find another cover. I'll say also R is equal to the union of the UX's for only the rational numbers x, for x in Q, the rational numbers. Hopefully you can see why that's true. And by the way, I guess I didn't emphasize this before. My epsilon on these intervals, I chose to be 1 over 1,000. I could have chosen it to be anything, larger, smaller, as long as it's positive. So basically, again, going back to U0, U0 is the neighborhood centered at 0, and epsilon, so it'd be 0 plus 0.001, 0 minus 0.001. So for U0, it would be negative 1,000 to 1,000th to positive 1,000, the interval would be. Now, hopefully this isn't difficult to understand why. If I take out all of the irrational numbers, the sets that have irrational number subscripts, and only include the rational number subscripts, why does that cover the real line as well? Well, take an irrational number like pi, 3.1415926, blah, blah, blah. We will have no u that is centered there, but we'll have one that is, we'll have a rational number as close to pi as we want to get. There will be actually an infinite number of rational numbers between pi and pi plus 0.001 or pi minus 0.001. So you can see that this is true, which means that R is a subset of that. So all we've shown here is that we started with an uncountable number of sets whose union contains R. Well, we took a subset of that. We took a countable number of sets, those indexed by the rational numbers. And if we take the union of those sets, R is also contained inside that union. So what we did is we took an uncountable cover and we showed in this case that there is a countable cover. But that's as good as we're going to be able to do. We're not going to be able to find a finite cover. If there were a finite cover, there would be, say, n of these sets, which means there would be one corresponding to the largest number of x. Let's say that was 1 billion. No, let's say it was 100, because I don't want to write all those zeros out. If that's the largest one in a finite one, well, that means that the number, every number greater than 100 plus 0.001 would fail to be covered. Hope that made sense. So this does not give us a finite subcover. So therefore, R is not a compact set.